Welcome. In this session, we're going to prove a couple of theorems that will be useful later in this course. The first is, if we have a linear form of a vector, what is its derivative? A linear form is the multiplication of a one form and a vector. We've seen that in previous sessions in this lecture. Let's state this as a theorem. So our theorem is that for any vector in a vector space and any one form such that the transpose of that one form is in the same vector space. Some authors will just say that the one form is also in a vector space. The gradient one form of the function that is the product of the one form and the vector is the gradient one form of that function at that vector is the one form. Before we do a proof, let's just check our units. The gradient is supposed to be a one form, and what we're saying is, in this theorem, is that it's specifically the one form that's here. Good, the units make sense. Let's pause and think of calculus. In calculus, if we had a constant a times a scalar argument t, then the derivative of a times t, if a is constant, is simply a. So this is starting to look as though it's the higher calculus version of something that we already know from basic calculus. Good, so the units match and our extension of calculus matches. Now let's do this as a proof. So proof, we know the directional derivative of the function with a vector argument is, so let's write down that definition. That's the limit as a scalar value goes to 0 of the level of the function plus the scalar times the direction minus the level of the function at the argument divided by the infinitesimal scalar. So what we'll do is we'll do something that we did way back in basic calculus. We'll substitute and we'll simplify. So that equals, so the derivative, the directional derivative of this function is the limit as h goes to 0 of, now I'll substitute the function. And the function is, we take the one form and we multiply it by the argument plus an infinitesimal amount of any v whatsoever. We subtract the function, which is a w, and we divide by h. Now let's distribute this one form across that vector sum. So that is the limit as h goes to 0 of a w plus a times hv minus a w divided by h. And we can take two steps at once, and that, well, let's take one step at a time. So here we have AW minus AW, so AW goes away. So that is the limit as h goes to 0 of the one form times h times v over h. And we can, that is the limit as h goes to 0 of, I can take this h out front, So I can say that that is h times, and now this is a scalar value, A times V, divide by H, and the limit of that equals the one form times the direction. And that has to equal the gradient one form of the function evaluated at any vector argument times V, because that's our underlying equality of the, so this is the definition of the directional derivative. This is the associated calculus equality. So that implies that A, because V appears in both, and this is a one form and this is one form, that implies that A is the gradient of the function at W. And we've completed our proof. Next, let's prove a theorem about a quadratic form. This quadratic form will appear often in this course. Our theorem is that for any vector that has n entries and any symmetric, so we'll always use B as a general symmetric matrix. So strictly this is B has n rows and n columns. Our theorem is the gradient one form of a function that is, so here is the quadratic form, is that is W transpose B W. So that is the gradient one form of this function will be 2 times W transpose times B. Let's do what we did with the linear form and pause for a moment and say that we'll first check, is this a one form? Well, this is a W is a vector, W transposed is a row times a matrix is a row, so the dimensions work out. In calculus, if we had something like b times t squared as our function, and we differentiated it, that would be 2 times b times t. So what would happen is we would take the 2 down, and we would reduce that power of t by 1. Here, what we're doing is we're taking the 2 down, and we're eliminating that vector and retaining that one form. So that's what we're doing. So what we'll do is we'll use the same method that we did for linear forms, which is we'll write down the limit and then we'll substitute and we'll simplify. And when we do that, what we'll need is this. We're going to need one fact. And the fact that we'll need is we will use U transpose B V, that is for any vector U and for any vector V, that equals V transpose B U. This doesn't work for a general B, it does work for a symmetric B. And you can think of that as being the way that you could go about proving this, and it would probably be a good idea if you did prove this to yourself, just to be really sure, is you could think of this as the vector U dot the vector that results from multiplying B and V, and that is the same as V dot the result of applying B to U. Because we can replace the dot products with these transposes and use the fact that B equals B transpose when you go through that proof. Okay, so that's what we're going to do. So what we'll do is let's write down the directional derivative, and we'll immediately put f, our function, in. So the directional the derivative in direction f of this particular function is the limit as a scalar value goes to 0 of f of w plus hv. So we have w plus hv transpose, so that'll be w plus hv quantity transpose times b times w plus h times v minus w transpose b w, all divided by h. Okay, so let's multiply this out. So that will be the limit as h goes to 0 of, that is w transpose b w, w transpose b w, and then applying this equality, we can write this next term. Here I've got a choice of how to write it. I'm going to expand it as, I'm going to take this w transpose b and bring h out. So I will say that is plus 2 times h times w transpose b times v plus h squared times v transpose b v minus w transpose b w, and that entire term is divided by the scalar h. Immediately I can see that w transpose b, that cancels out. I see an h appearing, so I'm going to do two things at once. I'm going to get rid of that, and I'm going to factor h out of this equation. And that's the limit as h approaches 0 of, so when I do this factorization, that's h times, that'll be 2 times w transpose b v, plus I factored one h out, plus h times v transpose b v divided by h. Well, the limit of h divided by h is 1. So I can now get rid of that whole limit. So that equals the limit as h goes to 0 of this interior term. So we'll bring that down. That's the limit of that interior term is 2 w transpose b v plus h times v transpose b v. And now we have to remember a simple fact about limits, and that is the limit of something that doesn't have h is that thing, and the limit of something of h times something, unless there's a division involved, which there isn't, but the limit of h times something is 0. So that simply equals 2 times w transpose b times v. And now let's put a bracket around that term, because that's a one-form term, and that has to equal the gradient of the function evaluated at w times v. So that implies that the gradient of the function at w equals this one form, which is 2 w transpose b. So what we've done here is we've written a quadratic form, we've recalled a result from linear algebra that is one of the many, many useful things about linear algebra. Then we simply formulated the directional derivative in its definitional form as a limit, and we then simplified and substituted and extracted the gradient from the directional derivative term.